So, welcome back, everybody. I hope you had a great weekend. And I wanted to give you just some quick messages, as we always do here. And the topic this week, if we just skim through, and you've probably seen from the email which we sent during the weekend to all of you. So if there's somebody who's not getting the emails which we send out in the weekends, please let us know. And the topic today is just a quick repetition from last week, just a reminder of many of the things which we went through. And then we are going to look at how to apply these things in the exercises when we're solving them. And we will have some repetition of this, the momentum and angular momentum conservation. We are going to look at examples which are relevant for the exercises. And then on Wednesday, we will continue with many of the same things. And we will also have a kind of split session. And we have two exercises which are relevant for the homework, both number 4 and the one which comes next week, number 5. On Friday, we are basically going to deal with the solution of the exercises. And one of the exercises is actually you having to add something to what you wrote in the program for homework number 3. And this is again going to be this bouncing object. But now we are not going to be happy with only this reaching the ground. But now we want to see how far it actually can get when it keeps bouncing. And then we have to make a model for additional forces. And these are the things which we are going to discuss during this week. And with examples and applications of forces, looking at momentum and energy conservation, and all these things which in a certain way make life much easier when we're going to solve equations, because sometimes we can just see from the forces that these are forces which will conserve energy. These are forces which will conserve momentum or the angular momentum. And that saves a lot of time when it comes to calculations. So I just wanted to very quickly remind you of some of the things we went through last week. And then I'm going to dive back again into the whiteboard, if that's okay. Yeah? So just a quick repetition, and you have everything in the slide material here. The exercises which we are going to look at on Wednesday, exercises which are also relevant for next week. And we have two examples. One which is a force which you have seen already. And then the other one is actually to show that this force here, which is very similar to the gravitational force, except that we haven't specified the constant gamma. So we're actually going to, on Wednesday, you guys are going to sit down and we are going to float around. And then we're simply going to see whether these forces are conservative ones or not. And what we need to implement then is actually the calculation of the curl of the forces. And we need also to have the forces to be something which depends only on position. They can depend only on position, but that does not mean that the curl is equal to 0. So it could happen that it's not equal to 0. So these are the two examples we will look at in more detail on Wednesday. So take a look at it if you wish to, and then we can discuss other topics related to the exercises as well. Then there's a drawing here. This is a little bit compact, but you can take a look at it. So this is the one figure to, yeah, I couldn't resist. And if you've seen that set of movies, you know where that phrase comes from. And I can rewatch this again and again and again. So my daughter and I, we have the time between Christmas and New Year's Eve. We just rewatch them, the extended edition of these movies. Okay, so this is a very nice drawing which Julie made. And take a look at it. I'm not going to spend so much time on it. But conservative forces are extremely important in science, in physics in particular. And it's a force whose property is that the total work which is done when you move an object between 2 points is independent actually in the path which is taken. So that's an extremely important statement. And at the end of the slides, you will find a reminder of what you might have seen when you took a math course on multivariable analysis, where we actually prove these statements. And it depends only on the spatial degrees of freedom, and it's possible to assign a numerical value for the potential at any point, and it leads to conservation of energy, as we have seen, and the gravitational force is one of these. And so we have a dependence only on the spatial degrees of freedom, but that's normally not enough. So one of the other properties which we have to fulfill is that the curl of the force is actually equal to 0. And these two exercises, which we're going to look at on Wednesday, they are examples of forces which will obey this relation here. Then the thing we did was to look at the total momentum. We looked at the momentum of two objects, and these are under the influence of some net forces. And these net forces could now be some external forces and some internal forces, and the sum of the external forces lead to two terms here, and the two internal forces, due to Newton's third law, they cancel each other. So that means that the total force, when you look at two or more objects, would be a force which depends only on the external forces in which these objects move. So this could be two objects moving in a gravitational field, and then they interact by repelling each other with some kind of electromagnetic force. So this was one of the things which we showed, and we showed that for more than just two particles. We showed that the total force is the sum over all the on an object when it's an isolated system. Then there are no external forces, and as an isolated system, we could simply sum up for one of the objects, I, the sum over the forces from all the other objects. And that meant that we could then find the acceleration acting on this specific object. So typically when you are going to run a calculation later for, let's say, the Earth-Sun system or the solar system, then the force on the Earth will be the force from all over the planets and obviously the Sun as well. And if you wish to be more ambitious, you could include moons and many other objects. So let's see. These are just some of the definitions which we went through last week. And then we could show actually that the sum, when we sum over all the internal forces, this is something which would sum up to 0. So the sum of all internal forces is actually equal to 0 when we sum over all the objects. Then that led to conservation of total linear momentum, which was one of the quantities we derived last week. And then we went on to look at the conservation of angular momentum. And in that specific case, we took up the definition of the angular momentum as an object which is perpendicular to the plane which is defined by position and the momentum, the linear momentum of a specific object. And we could then also show that in case if we had forces which only consisted of internal forces, then we could find that the derivative, the time derivative of the force, which is given by the torque, is actually something which is also conserved if we have just internal forces only, and internal forces which depend on the relative distance between the two particles. So in one of the exercises which we'll have this week, there's actually going to be cases where the total linear momentum and the angular momentum is not conserved. So you have to be a little bit careful. The force is a force which depends only on the positions, but it may not be something which conserves angular momentum. So we just have to be a little bit careful there. And the torque is then defined obviously as the derivative of the linear momentum here. So we are going to look at some examples now, and which are also relevant for the next homework set. But before that, I wanted to define another quantity which is very important for us, and which you will see being used again and again in classical mechanics and in physics in general, and that is the central mass position. This is a quantity which we often take as a kind of a support quantity when we rewrite equations. So later in this course, we are going to look at the gravitational force between the Earth and the Sun. And this is a system which we can solve analytically if we separate the variables in terms of central mass variables and the relative distance. And we can solve it analytically as a function of the relative distance. And we just leave the central mass. So this is a typical transformation which we often do when we want to manipulate equations. But let's bring some of these definitions up, and then we are going to look at examples which are relevant for the exercises. So let's try to do that. I'm going to switch to the whiteboard here. Feel free to ask questions here if you have any. Don't be timid, guys. So let's just do that and switch to the whiteboard. So there's one quantity which we didn't define last week, and this is actually the so-called central mass position. And this is a very useful quantity. So let's just define it, and then we're going to use it a little bit later. So the central mass is a quantity which has some interesting features if linear momentum is actually conserved. So the central mass is simply the position, or the average position, of a set of masses and this is weighted by the total masses, by the total mass. And it's a very useful quantity, as you will see later. So the total mass m is simply the sum of all the individual masses of all the objects which are present. Now, the way we would define it then is in terms of a vector, and it sums over the masses multiplied with the positions of the individual objects. And then we have a sum over I up to n, and this is divided by the sum over all the masses. And we are again assuming that the mass is actually time independent. And we can rewrite this as 1 divided by m, and then we have a sum over I equal 1 up to n, and then we have an mi times an ri here. Now, if the masses are all equal, so suppose you have equal objects, then you can obviously put outside the mass of the individual objects if they are the same. Now, the thing which is interesting for us now, if we now look at the rate of change, so that means the time derivative of the central mass position. So this rate of change as a function of time, so d of r of dt, that is obviously given by 1 divided by m. We are assuming that the masses do not change as functions of time. So we would have an m of I, and then we have a d of ri dt. And we know that this is actually the velocity. So this gives us the velocity of the system of v of I. And we know that the mass times v of I is the same as the linear momentum. So what we get then is that this is equal to 1 over n, and then I have a sum over I equal 1 up to n, and this is the same as the linear momenta. And you remember also that we defined this object here as a total linear momentum. So that means that what we have now is that this is the total linear momentum. So we can simply write this out as p divided by n. So this defines also something which is called the center of mass linear momentum. So it's just the derivative of the central mass position. And the central mass position is nothing but a weighted sum over all the masses of the objects divided by the masses of the object. This is just a definition, and it comes in handy when we are looking at systems where we don't have an obvious mass center. So then you can let this coordinate, when you have defined an origin, you can let this quantity r define a new central mass for the whole system. Now, when you're typically looking at the solar system, since the sun is something like 6 times more massive than most of the planets, except for Jupiter and Saturn, you can often think of the sun as the central mass of the system. That's a very useful approximation in many, many physics cases. When you guys are going to look at quantum physics, you will see that the atom and the electrons which are going around an atom, the atom is much heavier than the electrons. And then you can think of the atom as the central mass for that specific system. And in general, protons and neutrons have lower velocities than the electrons. And then you can really think of them as an object which is at rest. So physics, just keep that in mind. This is a kind of way of thinking. The physics is always about finding the right degrees of freedom. So if you're dealing with the solar system, you could say now the sun is much more massive than the rest. And then I would say the sun stays at rest. And then I let all the other planets orbit around the sun. So that would be my type of effective system now, where the sun is at rest. And I don't take into consideration the sun as a moving object. So the thing which is important now, if the linear momentum is conserved, as we have seen, if d dt is equal to 0, so that means that the rate of change of the central mass, the rate of change of r, which was just d of r dt, that's the way it changes with time, is a constant. It's a constant. Let me not do that. So it means that the central mass moves at a constant velocity. And that's a pretty useful thing. So if we have a system, like you will see in many physics systems, we will actually have forces which depend only on the spatial degrees of freedom. They will often be conservative forces. If we look at only internal degrees of freedom, this is actually what happens. So that means that the central mass of the system moves at a constant velocity. And that can, in many, many cases, allow us to simplify the equations which we're dealing with. So this is just a kind of a side remark, which I just add for the sake of completeness, because we're going to meet this quantity again and again. So the thing I wanted to look at now is a simple example, which is also pertinent to one of the exercises we're going to deal with in this coming homework. Any questions so far about what we did here? I guess you may have seen this before. Okay, so the thing I wanted to look at now is an example of how we can calculate the torque and look at cases where the torque may not be equal to 0. So what I wanted to bring up now is an example of how we use the formalism we have developed last week. So this is the torque. And this is a single object which moves under a specific field. And this is homework number 4 and exercise 4. So we have an object at t equals 0. So let's put it at t equal to 0 here. And then we have a position, which is now given by some x0 of I. This is the unit vector in the x direction. And then we have a y0, and we have the unit vector in the y direction. Now, what we do then, at time t equal to 0, we add a force in the x direction only. So now we just add a force in the x direction. And let's just write this force now as an F, and it's equal to an F of x, which is the strength for the amplitude of the force, multiplied with the unit vector in the x direction. And we know that this quantity is actually equal to dp or dt, as long as the masses are time independent. So this is something which we also discussed last week. So the thing we can do now is also that we need to define V0. So let's suppose now that V0 is actually equal to 0. And what we can do now, since we have the force, we know that there is a force in the x direction only. So we have an acceleration A, which is obviously given by F divided by n, and it acts only in the x direction. So what we would have now is when we integrate up, so this is again the same exercise which we have been looking at many, many times. So we would have a V0 plus, and then we have an integral from t0 up to t. We have the acceleration, and then we have a dt prime here because it's not the same time. Now, when we now put in the expressions which we have, we know that this expression for the acceleration is simply given by this f of x times I here. So in our case, the velocity is something which now changes only in the x direction. Since we started with a velocity, a position in the y direction, we have only a force which acts in the x direction. So that means that it's only in the x direction that we have a velocity which changes as a function with time. So then when I integrate up here, what I would get is that v of t is now equal, since v0 was put to 0. So this will be given by plus. We can just take that plus away. And we simply put an integral from t0 up to t. And then we have this f of x divided by n. And then we have a dt. So f of x is a constant. And then we would have this multiplied with an I here. And if we sum it up or calculate it, we get t0 was defined to be equal to 0. So this is simply fx divided by n multiplied with time and multiplied with the unit vector in the x direction. And we know also then that if we look at the momentum, so the momentum is simply equal to the mass of the object times v. So what we see then is that this is then equal to f of x multiplied with t multiplied with I. So that's pretty easy, right? Then we are just asked about the position then. So we had an initial position, and now we're being asked what is the position in the final as a function, what is the position as a function of time? And that means that we need to integrate up again. So we would have an R0 plus, and now we have to integrate from T0 up to T. And then we have V of T of dt prime. So you see there will be one term which is already time dependent. You also remember now that the R0 was simply given by a constant x0 times I. So these are just constants, y0 times j, the unit vector in the y direction. So that means that when I put in R0, I have a contribution in the y direction and a contribution in the x direction. But the only thing which is affected by time here is the part which has to do with the velocity. And we have no velocity in the y direction. So there's only a velocity in the x direction here. So that means that when I now integrate up, what I'm going to get is that R of t is going to be given by an x0. And now I integrate up the term which you see here, this term here. So I get obviously a 1/2 times t squared times f of x. So I'm going to get plus 1/2. Now I have to be a little bit careful here, because here, in this expression here, I looked at the momentum, but I have to include this term here, f of x divided by m, because the line below there was just the definition of the linear momentum. So what I end up with is 1/2 times this f of x divided by m. T0, we put it by convention, we put it to 0. That simplifies the calculations, obviously. And then we have t squared, and this is multiplied with I, the unit vector in the x direction. And then nothing happens in the y direction. So this is just a y0 times the unit vector in the y direction. With these terms here, we can now calculate the angular momentum. So the angular momentum in this specific case is given by definition by an object which is orthogonal by the plane, orthogonal to the plane, which is spanned by the position times the linear momentum. And now we have an expression for the linear momentum. And that means that what I need to do now is to take this expression here, and I have to take and calculate the cross product of that vector with this vector, which you see here. And that means that I have I and j components, which I have to take the cross products of. And since it's only one of these components which has a vector in the j direction, it means that some of these calculations will actually simplify. And I'm going to get a answer here when I plug it in, which gives me L is equal to, when I do the calculation here, I get minus y0 times f of x times t multiplied with the unit vector in the z direction. And now you see that if I take the time derivative of this quantity here, this is going to have a torque which is non-zero. So that means that angular momentum in this case is not conserved. So this is just simply going to give me y0 times f of x multiplied with k. So this object has a specific torque. And the torque is also orthogonal to the plane which is spanned by the position and the velocity times the mass, which is a linear momentum. So this is a typical example where you can extract these different quantities by one, integrating up and you find the velocity given the forces. Then you integrate up again and you find the position as a function of time. And then when you have the position as a function of time, you multiply that with the momentum. And then you have the angular momentum. And then you can see whether the system is something which leads to conservation of angular momentum, whether linear momentum is conserved or not. So this is a case where you have only an external force. So if you go back to what we looked at, there is no internal force here. There is only an external force. And when you have an external force, and if that is non-zero and time dependent, then linear momentum and angular momentum are not going to be conserved quantities. Okay, any questions to this exercise? So it's part of the exercise set which we have. And I hope you don't feel offended if I go through parts of the solutions. This is more to guide the eye, because we have now to bring in the different components we've been looking at. So sometimes, often the difficulty is actually to get started. So how should I actually start solving the exercise? And here we are given the force and the position. And when you have the force, you can calculate the acceleration. You integrate up and you find the velocity. And then with the velocity, you get the position. And then you can calculate the angular momentum. So this is a kind of basic steps which are important to think of when we want to recognize how to solve a specific physics problem. Okay, any questions so far? So what I wanted to derive now for you is another very important quantity. And that is the relation between the potential energy and the forces, which gives us another equation which we are going to use again and again in this course here. In particular, when we look at conservative forces, there is a very neat relation between a conservative force, if you have defined it, and a fundamental potential, which governs the physics of the system. So we have many potentials which are more effective ones, and then it's difficult to extract a force which we can relate to natural law. We would often parameterize it. But then we have specific forces like the strong force, the electroweak force, the electromagnetic force, and the gravitational force, which have a direct relation between the potential energy and the forces. So let's set that up, because that's an important relation which we will also need when we are going to look at specific problems now. So let's go back. That was an example. And now we need to discuss a little bit more about conservative forces. So what we have seen the following, that one of the things we need to make sure is that the force depends on position only, on the spatial degrees of freedom. Now, some of the exercises which you will encounter this week and also next week, and for the rest of the semester, may have forces which depend only on position, but they may not conserve energy, or they may not conserve angular momentum or linear momentum. But this is an important feature. Another one, which is equally important, is that the work which is done, W, when we look at the path here, C, so this is just to indicate the kind of path which is taken, F of R multiplied with a small displacement, this is independent of the path which we take. So this is a very powerful statement. And at the end of the slides, you will actually see a reminder of what you've seen in mathematics courses, where you actually go through the same derivations in terms of a line integral. And then you can also from that derive the next property. And the next property is that the curl is equal to 0. If these features are fulfilled, so like the first one and the third one are easy to find. Now, one of the things we are going to show now is the following. So if somebody gives you the potential energy, what we are going to show is that F of R is given by the gradient, negative gradient of the potential energy. So the potential energy is a scalar. Just keep that in mind. It's just a number. So kinetic energy is a number. The potential energy is just a number. And that's why you take the gradient in order to get the different spatial directions of the forces. So this is normally what we just call a number. And the force is a vector here. Now, the way we derive this is now to go back to the work energy theorem. This is the theorem we use, or I'd rather say, I never like to call it a theorem. I would rather like to call it a definition. So what we're going to define now is the work which is done by a displacement. Done. So let's bring in some definition here. By displacing an object and acting on that object with a given force. By displacing an object from a position R to a new position, which we just call R plus a small change d of R. And we know that by definition, this is now given by, so this small displacement, if we just bring back what we defined here. So let's just write this down as an R, the work done by going from R to R plus d of R. This is something which we defined as the, in terms of an integral, or rather this is the force acting on a small displacement. So it's F of R multiplied with this small displacement here. This is the small piece, and then we would integrate that up. And what we have done then is actually to define this quantity. This is now defined as minus, when we now calculated the kinetic energy and put it up. So this is given by V of R plus D of R minus V of R. So let me just quickly remind you about that. If we have a conservative force, now we are assuming that we have a force which conserves energy. So back to last week, let me quickly remind you of that. So what we showed then was that the kinetic energy difference between V1, this is the velocity in a position x1, minus a half times V0. This is the work which is done by moving from 0 to 1. And we could show that that was given by the difference in potential energies. So that was given by 1/2 of K of some potential energy, V at the position x0 minus 1/2 of V at the position x1. And the example which we used for the potential energy was this spring force. That was a typical example which we looked at last week. If we want to deal with a gravitational force, the calculation becomes a little bit more involved and complicated. And that's something which we are going to look at on Wednesday when we do the exercises with a force in 1 dimension, and then we switch to 3 dimensions. So but you can show the same thing if this was the gravitational force. So these were the things which we looked at last week. And then we had a force, in that specific example, we had a force which was F of X, which was simply given by a spring constant. And in that case, what we ended up with was that these terms, this term here, and this term here, they were simply given by, sorry, there shouldn't be, I anticipated things, there shouldn't be a factor of a half here, sorry. So if we did that, we got 1/2 of k times x0 minus 1/2 times k of x1 squared. And then what we could show is that the total energy was conserved of V1 squared plus 1/2 of k x1 squared was equal to 1/2 of m of v squared, this is a v, plus k divided by 2 of an x0 squared. So last week we simply inserted a force which depends only on the position. We can also show that this force is a conservative force because the curl of this force is going to be equal to 0. Actually, you don't need to calculate the curl here because it depends only on x, right? So calculating the curl of something which depends only on one dimension is going to give you a curl which is exactly equal to 0. So this is a case where you don't need to do any calculations to get the curl of the force. The gravitational force is a little bit more complicated because you're going to deal with 3 dimensions then. But this is a kind of demonstration we did of a so-called conservative force. And we found then that energy was conserved. Potential energy plus the kinetic energy at an endpoint was equal to the potential energy and the kinetic energy at the beginning point. Now, what we are going to do now is to use this assumption again. And we are simply going to go back to the equation which we have here. So what you see here, this equation here, is nothing but the one which I wrote a little bit down here, this term here. So what I can do now is the following. So let me just bring this up again. So we have, for this very, very small displacement, we have a V of r going to r plus d of r. And for this small displacement, this is given by the force acting on this small displacement. And this is given by minus v of r plus d of r. And it has a minus here of v of r. And now we're going just simply to rewrite the force in terms of x and y and z components. So we're going to have a vector for the force multiplied with a unit vector and multiplied with displacement. So this gives us Fy of dy plus Fz times dc. Then the next thing I'm going to do now is to manipulate the expression for the potential energy. And again, what I'm going to look at is the expression which you have here. So this one. So let's take that expression and rewrite it. So I have a potential energy of r plus d of r and minus v of r. And this is nothing but something which we can rewrite now in terms of the different components. X plus d of x, y plus d of y, and then I have z plus dc minus v of x, y, and z. So let me know if something is unclear here. Right? The next thing I need to is to go back to some of the things you guys did in multivariable analysis. So if we have a function, suppose we have a function f, x, y, and z, then we know that this line element d of f is given by the partial derivative with respect to x times d of x plus df dy of dy plus d of f of dz times dc here. So the what I'm going to do now is actually to define this change which I have when I go from x plus dx, y of I plus dy to z plus dz. I'm going to define that as the change in V. So what I'm going to do now is simply to say that this V of R goes over to R plus D of R, which is given by the distance which you have here. So this quantity is something which I now will label as a minus dV. So the quantity which I'm looking at is, so this V, R goes over to R plus D of R, is actually given by this difference which you see here, and it's given by the minus of that difference. So this is again equal to minus, sorry, I'm going to put the minus outside here, minus here, and I have a dV dx times dx plus a dV dy multiplied with dy here, plus a dV dz. It's not the most exciting exercise we're doing, but keep in mind now that what I did, this more compact way of writing it, this specific way which you see here, is the same as what I wrote here, or this quantity here. And then I bring up the definition of a function and the line element here. And by going back then, I know that this is V of R plus D of R minus V of R is now equal to the force multiplied with this displacement. So what I'm going to do now is simply to take these elements here and equate them to what we have down here. So this should now be equal to D of the force, D, sorry, we just go up here again. So we have the force, let me just, I was a little bit too fast here. So this is equal to F of X times D of X plus F of Y times D of Y plus F of Z times dz. And now you see that this term is equal to that one, and to that one, except that we have to pay attention here because there's a minus sign in front of it. So that simply means the following. It means that F of X is equal to the minus the derivative of the potential with respect to X, and the potential now depends on X, Y, and Z. So that's the partial derivative. F of Y is given by minus dV dy. And finally, I have F of Z, which is equal to minus the partial derivative of the potential with respect to Z. And if I collect all these, I can then simply rewrite that F is equal to minus the gradient of the potential. And that's a very, very important relation, which we will use again and again and again. So if it's not uncommon that you, so it's not uncommon that you will be given a potential energy, and with that potential energy, you can derive the force. So in many cases, you won't have a so-called force of nature, like the gravitational force or the electromagnetic force, some of these kind of fundamental forces which we have in nature, but you will have some kind of effective force. That is pretty common. So if you're dealing with the field which is called molecular dynamics, which is a popular way to simulate materials with billions and billions of atoms, you're actually solving this by calculating coupled differential equations using Newtonian mechanics. And in that case, you need an effective model for the interactions between the atoms. And this becomes an effective potential, which you can derive from experimental data. And when somebody gives you an effective potential, you simply take the gradient and then you have the force. So going this way from having the force, which we have here, now the potential as you have here, and then taking the gradient gives you the forces. And with the forces, you have the acceleration. And when you have the acceleration, you can find position and velocities as functions of time. And then you can actually solve the equations of motions, and you can see how the system will behave as a function of time. And this is at the end what we normally want to see when we run a calculation in mechanics, in classical mechanics. So it's pretty common when we don't have a fundamental force, and normally we know the mathematical expression for a fundamental force, is to derive what we call effective potentials. And these can be derived from experimental data. There are many ways of doing that. And then when you have that expression, you take the gradient and then you have the forces. And then you can run your calculations, since you have the forces and then you get the acceleration here. Okay, so I see time is running fast here. It always runs fast when you're talking about fun things. So one of the things I wanted to bring up again then is a new example. And this is connected with homework number 4 and the last exercise. So that's the numerical exercise. And now we're going to use this kind of work energy theorem to see how we can actually extract things like the velocity, the position of the object, and so on. So let's now assume that you have a ball which is falling, and this ball now hits the ground. And let's now assume that we look at two phases. One, when it's only falling, right? That's phase 1. And then we look at phase 2, when it actually hits the ground, and see how we can model the way it hits the ground. So this is a falling object. So it could be a ball. And we are going to define a phase, which we just call phase 1. So let's now draw a coordinate system here. So you could think of this as the ground along this axis here. And the object is falling down. So we call this a phase 1. And it's just falling down here. And if we now take away, so in the last exercise you did last week, you added an air resistance to it. But let's just assume for simplicity now that we only have the gravitational force. But you've made it more complicated by adding a model for air resistance. So the gravitational force, as we know, is a fundamental force. So what we have then is an object which is under the influence of the gravitational force, and that's simply given by minus m times g and multiplied with the unit vector in the y direction. Then we can look at the phase 2 here. And this is a case when this ball hits the ground. So let's suppose it gets some kind of deformation here. And in our case now, we still have the gravitational force, like this. But then there would be something else here when it hits the ground. What would we normally call that type of force?
Spring force.
Yeah, exactly. Spring force or normal force. Just a normal force. That would be the typical name we would put into it. So that means that there would be something like a normal force here, acting upwards. Now, what kind of force is that? Is that a fundamental force, or what would we typically call that type of forces? When you get in touch with something. Contact forces. Excellent, excellent. So the typical thing which you will see in most of the cases we deal with is that we have no fundamental force for the contact forces. So a topic like friction is a topic which is a wide open research topic. And depending on what kind of objects are sliding on top of each other, friction may depend on temperature. It may depend on the type of materials which are sliding on top of each other. If you're dealing with tectonic plates, there's one type of friction. If you're dealing with a material on a table, it will be another type of friction. So we don't know, right? So that means that when we are going to solve this exercise, we need to make a model for the forces. what could be the simplest possible way you could model this normal force? If you now think of a ball which hits the ground, and it's a little bit, not exactly jelly-like, but it goes a little bit like this, right? Yeah?
You need like an if statement, like if the ball is touching the ground.
Yeah? How would you model this, the normal force? So any good suggestions? Spring force, excellent.
Thanks, guys.
So in this homework, yeah, you said so. I mean, it's my hearing, right? Sorry for that. Now so the way you would actually do this in the homework now is to try to come up with a model for the natural force. And the most natural thing you can do then is actually to model this with a spring force. And that's what you would have to plug in your program. So in your program, when you're going to model the bouncing of the ball, you have to find a way to say that, okay, the distance now is so that I've hit the ground, and now it's gonna bump up again. And then you have to add this force. And when the height of the ball has gone beyond a certain level, then you say, okay, this normal force is not at play anymore. So I see that my time is over. This is the topic which we will discuss on Wednesday. And then on Wednesday, after we've done with that, we are going to look at these two exercises and calculate the curl of the forces. Okay. So I'm going to stop the recording for everybody.